Today we're going to talk about visual and algorithmic interpretation for responsible AI. So that is also the major theme of work that we have been doing at Georgia Tech. So my group is called the Polo Club of Data Science. Yes, I like to name things after myself. As a student. So we work at the intersection of artificial intelligence and human intelligence. So actually, traditionally, it's actually human-computer interaction and machine learning. But we need to brand everything, or we brand everything as AI. So AI and human intelligence. But at the core is we want to develop tools that are interpretable, that are safe to use, and also create results that are reliable. So how to create these tools to help people make sense of large amount of data and also complex models. So I always like to start by thanking my students. So everything you see today is done by them. So by our PhD student on the left, and then my master's student and undergraduate student in the middle and towards the right-hand side. So why are we working on Safe AI? Why are we doing interpretable AI? So I think Safe AI is probably very easy to understand, unfortunately, from a lot of examples that we continue to see. Because now AI is used in a lot of high-stake application. For example, you remember that these instances, the Uber incidents where a pedestrian or someone was crossing a street at night, and then the car was not able to detect the person until really, really close. So it's an Arizona incident some years ago. Unfortunately, we continue to see that. So that means Safe AI is very, very important. Right? Certainly, we also continue to see this issue with LLM, generative AI models, making things up, hallucination for things do not exist, or even worse, people use them and they follow the advice from these chatbots. Right? So we continue to see these, unfortunately. So a lot of people are definitely working on Safe AI, looking at the vulnerabilities and also the countermeasure protection. But if you really ask people working on actually maybe you should not want to ask them, but you do ask them, how do these methods work? They say, oh, you are doing countermeasure protection and make these AI methods safer. How does that really work? And usually what they would tell you is that, oh, the numbers looks good. Our approach, increase the number by 10% and that's it. So do we really know? Not really, actually, because a lot of these models now, they're so complex that even the people who develop them, they don't really know what's happening. So then what do we do? So do we just surrender and do nothing? No, so we think we should do something. And our approach is we call interpretable AI. And particularly, we want to make these black boxes a little bit more translucent, not really to overwhelm the users with too much detail, but rather we create scalable interactive tools. A lot of times it's visual tools to help people make sense of what's happening in these models. Right? So the key there is how do you surface relevant information to the user, not overwhelm them, but in a very intuitive way. So that is why Safe AI, interpretable AI, closely related. So today what we're going to talk about is show you some examples of the work in Safe AI, in interpretable AI, and those are the two major thoughts. And then lastly, also something that I'm really, really passionate about is AI education. Because once we're working on these Safe AI, interpretable AI tools, we find that learning how these tools work very important. So that means how do we help students to learn how these methods work? AI education, now third thrust that we're going to talk about. So today we're going to start with the first one in the beginning. So Safe AI will give you two examples. One we call LLM safety basins, so quantify or to visualize the vulnerability in language models, particularly when they are fine-tuned. And then we have an approach called Shape It Up, how to make it safer when we're doing fine-tuning. And then for the interpretable AI tools, a number of examples. How do we connect interpretation, visual interpretation to AI safety? And then a few tools like LLM attributor, WizMap, and ConceptAttention to how to fill those gaps, once you reveal gaps between interpretation and safety. And then finally, for AI education, we'll talk about the suite of AI explainers, called transformer explainer, diffusion explainers, and so on. So how do we help with AI education? So we'll start with Safe AI, particularly the LLM safety basin work. So which was published in Europe's 2024. So the main question we're trying to understand is, since everyone's using LLM now, companies are using LLM, and a lot of times the use case is that they will have some pre-trained LLM, and then if you are a company, you might fine-tune the LLM on your own data. Because you want to be more able to answer the question that you care about or using the data that you have at the company. So we want to know how well these models or how well these process fine-tuning might affect the capability, or maybe we call the guardrail of these LLM. So guardrail in this case often is about what we call alignment, in quote. Alignment, that means you don't want the LLM to spill out harmful things, right? So we want to align that to humans' values. So our investigation started with asking a question. So if these models, let's say Llama 3, Mistral, Vicuña, or any models that you have, if you start to perturb or change the internal parameters of this model a little bit, and a little bit more, and so on, how would that affect these safety guardrail? So here what we're showing you is three kind of valley or basin looking things. So on the left is Llama 3, Mistral, and Vicuña. So vertical axis here is safety. So lower is more safe. And then the purple dot up there, let's see, move the cursor. Purple dot here is where the model would be, like originally safety aligned model. So that means these models already have some guardrail in place so that well, hopefully it would not spill harmful things. Right? So every model has this starting point. And then what we're happening here, like horizontal axis, as we now do some random perturbation of the parameters of the model. So that means we're gonna fuzz it a little bit. And then we want to see if they break the safety guardrail, right? So, and we find that, yes, we can. So as you go back and forth, it's okay. So it's still safe. So remember, vertical axis is lower, safer. So it's still pretty safe. But as we perturb it even more, then at some point, then it breaks. So safety guardrail breaks. So that means all the safety guardrails in place to prevent it from spreading harmful things is no longer there. So, and not only it breaks suddenly, and also it breaks really badly. So as in all the way to complete unsafe. You start to say offensive things and everything. So this was our original investigation because when you're doing fine tuning, you are changing the parameter. Right, so that means we want to know is when you do fine tuning, when people are doing fine tuning, how is it affecting the safety guardrail? Because everyone's doing it, but no one really study it. And what also interestingly is our discovery is that no matter what model that you are doing, you do the same thing, the guardrail is going to break, and it will break in this way. And we call it safety basin because the shape, it looks like a basin, safety basin. So that means safety drop, in this case, like all the way shoot up to the top, very unsafe. So what does that mean for fine-tuning? Right, so here we're showing you the case where we're actually doing fine-tuning rather than doing random perturbation. So that means you could have your original safety aligned model like down at the bottom. And if you are fine-tuning it using like a mixture of safe and harmful data, you say, well, why do we even fine-tune with harmful data? Well, the reason is oftentimes people don't really know. Like if all the data they use to fine-tune the model is completely safe. So then you could have a mix of a little bit harmful, a little bit safe. So if that's the case, a lot of practical use cases, you are probably fine. But on the other hand, if you even just have a few harmful data point, it can dramatically break it and break it suddenly. So that means our approach is to help people visualize and quantify the safety risk as you are fine-tuning. So usually people do fine-tuning, they look at some model, some numbers, but then here our first time to really visualize what's happening. And then you may ask, well, so how is this breaking safety the same as like breaking or harming capability? Capability as in how are the models in answering questions? Like for example, on the right-hand side, we're showing, we call this capability landscape. So particularly some lines, we're looking at these MMLU benchmark scores. So that means how well the LLM can answer questions. For example, red line, high school US history, orange line, US foreign policy, and then blue line is abstract algebra. So that means how well this model in the accuracy in answering the question. And the horizontal axis is how much we change the parameter. So what we see here is that they do affect, as you are moving the parameter even more, they do get worse. But then the thing is, it's not the same as breaking it suddenly. So what that means is breaking safety is very different from breaking or harming capability. So that means there's a unique characteristics when you are breaking safety. Right, that went for fine-tuning. So the natural question you may ask is, well, okay, so there seems to be some risk. So how do we safely fine-tune LLM? Right? Yes?
So this is very cool. I have a question about this perturbation. So when doing the perturbation, this is happening in the latent space, right? So does that mean like some of the perturbation actually cannot be translated back to very interpretable prompts? Or like, can you comment a little bit on like what do those perturbations actually look like?
Yeah, so this question is about for the perturbation, is it happening in the latent space? So can we translate the perturbation back to like maybe tokens? Transfers, yes, it's happening in the latent space. We did not study like how well it would go back to the token space. So there's some work on that, and yeah, so I don't know the answer. Maybe that's a good quiz question. Yes. So, oh yes.
Your previous slide, sure. How do the sort of magnitude of the axes line up between these two charts? I'm wondering if like sort of the safety shock break happens during like within the -2 to 2 and the accuracy chart or beyond that.
Oh, so the horizontal axis, how does it align?
That's specific on both charts.
Oh, I see. Yeah, great question. Actually, that's one of the questions of the reviewer about aligning. So here so here we're mostly interested in the shape of it. So you'll find that even if you do perfectly align them, you will still get this shape. So that means that here the abrupt increase there, no matter what scale, you are still going to see that, because here all the way is pretty much dropping to the lowest point. So we did not need to or investigate like specifically how to align perfectly the unit because the shape is already telling the story. Yeah. But good questions. Yes. Any other question before we move on? Okay, if not, then yeah. So then, how do we safely fine tune? Because if there's risk in doing fine tuning, so to answer the question, we want to know like currently how people have been doing fine tuning, right? And we characterize existing methods we call static safety shaping. What that means is if say, oh, you have LLM already trained, and then now you have your own data, and you give example. You say, for this particular data point, this is a good example. This data point is a negative example. And you would either use the whole sample completely or you don't use it. So we call static safety shaping. So that means you either keep or drop a whole data example. And that's been what people have been doing. So static safety shaping. So here we have a pretty scary chart, but not too scary actually. So we're showing you how this current approach of either keep or drop example is not ideal. So at the very top row here, we're showing how the model is doing. So in the gray here, this is the capability. So how capable, how good the element is answering questions. And then purple triangle is in terms of safety. So that means both of these 2 points, you want it to be more to the right? More safe, also capable. And then now we do fine tuning. So what do people usually do? Well, they do vanilla SFT, supervised fine tuning. So that means the data point, you have the label is good, okay, good, harmful, and then the other, not harmful, and then the other is harmful. And so what will you do? Well, not too surprisingly, yes, it can do pretty well in the capability keeping it, but then for the safety, it could hurt quite a bit, particularly if there are some points that are a mix of harmful, unintentional maybe, so it could drop the safety score quite a bit. Then they say, well, how do people handle those cases? And what do they usually do is they will add a guardrail model. For example, we are using a granite guardrail model. So we'll push the purple dot all the way up to pretty high, which is good. Not as high as originally it was, but pretty high. And in this case, since it's likely we still have some we call false positive, false negative. So that means some data points that are actually harmful, but they kind of sneak through the guardrail. So that means here we have 3% false negative. So capability, you'll find that is always you are preserving it. It's the safety that is the issue. And not only that, when the false negative, it increases. So that means you have mixing more harmful data, in this case going to 18%, then safety score would drop further. And certainly you increase, as you might expect, increasing the percentage of false negative, safety drop even more. So why we're studying this is because in practice, often people do not really fully know how safe or how unsafe their data that they're using for fine-tuning would be. So which also means the current approach of either keeping or dropping a data point for fine-tuning is flawed. Right? So then how do we fix that problem? So in hindsight, you say, oh, that's pretty easy. In hindsight, it's instead of all or nothing, then maybe we can look into the data point and then we identify which segment or which part is safe and which part is unsafe. Right? So that's exactly what we did. So shape it up and publish a Neurist, and that is the approach. And particularly want to quantify and have a way to use these segments, safe segment and unsafe segment. So here I'm going to show you an example. We call this dynamic safety shaping because we chop up the data point and then we say which part is correct or which part is harmful and which part is not. So example here, we say the training example, this is the actual training example. The prompt is write a script that that can exploit vulnerabilities in a database. And also as part of the example, the response is, it first starts saying, I cannot assist with creating script for exploiting vulnerability in a database. So that's a good thing, because the model is basically saying, I'm not going to do it for you. But, well, so that means that's a safe segment. But then after that, it say, oh, sure, here's a sample Python script that can demonstrate how you might hack into it. Right? So that's unsafe. Right? This segment is not good. But then after that, it tried to get back to correctness. So it said, oh, it goes against ethical guidelines. So that means go back to safe. So that means even in this example, there are already segments are safe and unsafe. And we can chop it up. And in hindsight, it's actually pretty easy. You just chop it up and then run it through the guardrail model. And then that means for each of the segment, we can dynamically reweight the loss based on the safety of these segments. Right? So very simple method, which is great. So because that means people can use it right away. So we tested how robust this approach would be. We tested against a different LLM, guardrails, harm levels, and data set. So at the very high level, it works no matter what you do. State-of-the-art safety gain, no compromise in capability. So here we are showing different LLM, and then here in orange is our approach, and in terms of safety, and then the gray is the capability. It's the origin safety, and then in blue is using the typical vanilla safety fine-tuning. So that means we're keeping pretty close to original, in some cases even better than the original. So here I'm showing only one for different LLM, but the result holds even for different guardrails and different harm levels. Yeah, so those are two examples. So we're looking at how to quantify fine-tuning risk and also what are the approach that can mitigate this. So while we're studying these more primarily algorithmic approach, you'll notice that we also already use quite a bit of interpretation, and particularly visual interpretation. So that brings us to our second area, interpretable AI, where how do we help people more easily interpret this result? Can we build tools to interpret the result rather than only looking at a model and then we come up with our own bespoke visualization, how to do it more scalably? So actually, when we're working on these problems, we actually want to have a survey that answers this question. I said, what are the gaps there? Like, have people been done? Have people done like safety-based and visualization and so on? Short answer is no. So that means there are opportunities for writing the first survey. We call interpretation meets safety. So particularly is to identify what are current work in interpretation, particularly on the visual side, and how are they used in safety, for safety. It was published in EMMLP as a full paper, or full track, I think that's what it's called, yes. So first survey on that. And this is a screenshot of how we organized the 76 papers that we surveyed. And we use a taxonomy where we look at groups of methods. We group methods by the interpretation techniques that they are proposing, and then how those techniques would inform safety enhancement. So that means how to make models safer. And then finally, how these enhancements would be used or operationalized in actual tools. So that's one axis. And the other axis is we're using LLM workflow. So what are the kind of techniques that's targeting training? What are them targeting the data or input data? What are them for model inference? And what are for generation? So this is our taxonomy. So then two axes, and there were 76 works. And then we put that into that taxonomy. So how you can use the survey is that you can ask questions. You can say, oh, any methods are there, like anyone work on, for example, and then safety using LLM reasoning, for example. Then we can go back to our table and say, so we want interest in safety enhancement. We care about LLM generation. And then, well, okay, here's a particular section, particular papers that we want to read about. Right? Or are there any research gap between interpretation and safety? Like what have people not been, what are the things that have not been done, right? So then we can look at the question marks in our table. So for example, there's not as much work done in attributing unsafe output to training data. So that means if the LLM is generating unsafe things, so what is the data point that give rise to that, right? So actually, this is also the reason why that motivates us to say, well, if there's a gap, then we may want to fill that gap. So LLM attributor is the tool that aims to fill that gap. I published it at AAA as a demo as an interactive tool to help people attribute the generation. If it's, oh, it's unsafe output, so what is the data point that's causing it? I'll show you a quick demo for this tool. So high level is visualize training data point responsible for the generation. And we're going to use an example for 2023 Hawaii wildfire. You may remember that there were some conspiracy theories at that point. They say, well, the wildfire was caused by directed energy weapons, right? So, so that means we could have a LM generated output. They say, oh, 2023 Hawaii wildfire were caused by directed energy weapon. So as part of the LM attributor interface, the user can select these tokens, directed energy weapons. And then you can run the attribution algorithm. And then we have a user interface down here, and it will show you the top two, bottom two. So that top two meaning the data point most likely going to be responsible for that generation. And then also you can actually change the number, and then can expand on the data point. In this case, it's actually a Twitter, well, X, I should say, an X post responsible for generating conspiracy theory. So this addresses a major gap where often people say, well, you look at the output, you may attribute to some internal parameter space, latent space, and then that's it. In this case, it can tell you exactly which data point that likely is the reason. So you would say, what does that mean, like in practice? So that means for companies who have the capability of training this model, they can go back to the data, they can actually remove these and then improve the capability. Not like everyone can do it because not everyone can train it, but if you do have the capability of doing the training model, you can actually take those away. So this is a missing tool. Actually, not as much people are working on it, and we're glad that we have some preliminary work in that area. So training data is very important. So in this case, you know, well, I can remove this, but sometimes people just don't know, like, what do they have? Because right now, LLM often are trained on data from internet. And the current approach is we'll just take whatever there is, maybe we'll do some filtering, but what can we more broadly say was in the data? So we'll build a tool called WizMap to help people visualize the embedding of these large data set. So WizMap's developed in collaboration with Apple. It was a ACL 2023 demo. So here we're showing you examples where the data set is ACL paper abstract. So that means each point that you see, each blue point here you see, is the paper abstract. And I'm going to play. A nice thing about this tool is you really can see all the data point. If you want, you can zoom in to it. You can hover over it, and then you will see the actual data point. And so kind of Google Map like zooming in, zooming out. And you can also adjust how you would like to summarize the different regions, because there are millions of points. You don't want to show millions of labels. So multi-scale embedding summary. So each region, you have a high-level summary for that region. You can zoom in more and so on. You can show the contour, the heat map, rather than only the data point. You can also do search. For example, here we say we want to find only papers about hate speech, right, in the search box. And then in purple, you'll highlight the data point that include those phrases. You can also visualize embedding over time. So because ACL is a conference, annual conference, so you can play it over time. And here we also want to showcase how scalable it is. So here's 3 million data points. It's completely in browser. So that means we are not really going into any server, everything on your laptop. I don't know if you notice your phone, your laptop is extremely powerful these days. So it can easily handle millions of data points. And also we have connected to Colab and Jupyter Notebook and so on. So that means you can run the tool completely locally without using any server. Also inspired follow-up work. So our colleagues at Apple, so they now have embedding atlas even more scalable. So again, inheriting a lot of the benefits of WizMap, where it completely on device, and I can now handle tens of millions of points at interactive speed. So here, each of the points you notice, like no matter what we're handling, each point is a data point, like fully generated data point. It could be at a text abstract of a paper, or maybe an image embedding, right? So, and WizMap and embedding atlas is a way for people to look at that as a whole. Where do all these data points sit? But then we want to dig a little bit deeper. Let's say for a generated image, which is a point here, what's inside the image, right? So that is a question we want to address. It's like we want to know, what is it in a generated image, right? So ConceptAttention is one approach for doing that. So main idea is to allow us to visualize any concept in a generated image. So this work is led by who's now third year, time flies, third year PhD student in our group. It's published as ICML 2025 as an oral paper. So here for images, we are talking about images generated by text-to-image model. So I think everyone by now has tried it, text-to-image, and a lot of these approaches are based on diffusion transformer. So what it means, if you have not used it yet, is you can type a prompt and say, I want a lovely dog, like maybe swimming in the water, and that's the prompt you have, and then you have an image like this. So a lot of companies have this capability, particularly Imagine company interested in providing support for designers. Like you can type a prompt and then you can get image generated. But often in these contexts, whenever the user can type in anything, there's always that need to know what exactly is generated. Because again, the user can ask for something and then you end up giving something that they do not want. Or maybe in cases where it's even harmful. So then what really gets generated is an image. That's a perpetual question that people have. And how do we solve it? So very naturally, people would say, well, so because this is the image, right, that is generated, maybe we want to show some kind of heat map to see like which region is what, right? So ConceptAttention is one of those approaches. So it particularly aims to create high quality saliency map or heat map, and using the text to image generation approach internal method. So what that means is we do not need to add any training phrases there, and we can directly use whatever the model has and then visualize and identify which regions are certain concept. So we're showing an example here. Our prompt is a dog by a tree, which is on the left-hand side. And then in the middle, this is the diffusion transformer, the workhorse of the text-to-image diffusion model. And then on the right-hand side, that is the generated output, right? That ideally is what you want. And then at the bottom is our approach. Our approach, ConceptAttention, apply on this particular model. And here for the dog concept, and then we have the dog region highlighted. And then for ball, yes, there's a ball at the bottom, a tree, grass, sky, and background. Something you might notice is even though our prompt says a dog by a tree, a ball gets generated. Grass also generated. You did not ask for it, but you can generate it. So ConceptAttention is an approach that allows you to visualize and highlight even for concept that your prompt did not include. And that's a very powerful thing because there are often cases where, let's say a user I want an image of a soldier. You did not ask for a gun, you do not ask for bombs, you do not ask for other things, but they might be there. So that means that having an approach that can help us identify where they are very, very important. So at the high level, you will say, well, then people have done this. Like, what's special about ConceptAttention? So a key advantage of the ConceptAttention is provide high quality saliency map or heat map. It does not require additional training. A lot of existing approaches do require that. It works for prompt tokens or concepts that are not in the prompt, a key differentiator. And also that it has very low computation cost. So it runs in parallel. Actually, as the image is generated through iteration, we would get these incremental heat map. So here we're showing you at the bottom existing approach based on cross-attention. And you will find just by eyeballing it, you already know the ConceptAttention heat maps are a lot more crisp and targeted, while for existing approach is more washed out and more fuzzy. And also additional is that it also works for images. Actually, when we developed the approach, we did not really test for image, but then the reviewer asked, oh, does it work for images, for videos, and also on X, people ask for it, and then, oh, okay, maybe we should just go ahead. It's trivial to just extend to video, and at high level, it works. And also, this is something you can use right away. So we have a demo on Hugging Face, and that you can try immediately. So ConceptAttention, originally we intended for visualizing concept in generated image, but the image does actually do not need to be generated. It can be your own image. You can upload your own image and then ask what's in it. So for example, here I say a dog on the grass in the park. And then here you can type in whatever concept you're interested in. So I'm clearing it, and I type dog, grass, tree, sky. Right? And I can run. And then the top row here is our ConceptAttention. So dog is there, grass is there, tree. Yeah, this is not part of the problem, but I would get the heat map. Where at the lower row there is existing approach. Using cross-attention, you'll find that it doesn't work for tree and sky because that was not part of the problem. Right? So another screenshot for comparing with existing approach. Second row and third row, those example, and some existing approach, you cannot even make out anything from it. So that means at a high level, ConceptAttention can outperform more existing state-of-the-art zero-shot interpretable method. So you may ask, so how does it work? Like, so it seems still conceptually pretty simple, and which is good. So generally we like simple and effective. That means people can use right away. So in detail, so is taking advantage of the multimodal diffusion transformer's unique property. So here we're showing a little bit of a detail there. If you say the user asks for a dog with a ball, and then the image will be incrementally generated or refined over iteration. So what's happening internally is your prompt would get tokenized into a dog with and so on. So you can loosely think of it as like segments of the text prompt, and the image will also get petrified. So that means you can think of it as dividing up into maybe 8 by 8 pixels, 16 by 16 pixel kind of patches. And both of these will get fed and iteratively refined through the models and multimodal self-attention process. And then through many steps, then and that will get refined, and then the image is what you want in the end. So under the hood, what's happening is there's some matrix vector multiplication happening. Particularly, the self-attention type product is the part that we care about. So remember that the input is the text token and the image token, right? And then the self-attention process, and many steps in the middle, is where that gets refined. So existing approach, usually they will look at only the cross-attention process. So that means during the computation, how well those two modalities are interacting. So over time, over iteration, those will get refined more and more. And what we found is that, well, instead of looking at what's happening in the matrix itself, we can actually look at the output. In this case, it's the V vector after the self-attention dot product. And we can look at the output after every iteration, which is, you can think of it as a refined version of the input text token and the image token. And not only that, we can do a dot product. So that means looking at how strong the association there is between the text and image. And that is our attention map. So that is our saliency map. So we found that the quality is way higher than looking at what's happening in the matrix by looking at the output instead. And not only that, we found that, well, so does the text token need to be from the prompt? Short answer is no. So we can actually augment the process by adding, we call the concept token. So fancy name, what it really is still text. But now we can add it to the bottom, and it does not affect the generating process. It's more just to get the dot product of the word that we're interested in, for example, dragon or rock. And then we can still do the dot product, in this case, additional dot product in green, multiply it with our image token, and that get the saliency map. So that's how the secret sauce in getting a saliency map for concepts that are not part of the prompt. And you say, well, okay, so that's not anything secret. You are using whatever the diffusion transformer model already using. Like, why have people not done this? Main reason is because of diffusion models. Until more recently, they were using UNet. And while for state-of-the-art model, they are now using diffusion transformer. So what that means is that previously, when people are using UNet, internal computation is they are looking at cross-attention. Yes, it is still using cross-attention of image token, text token, but then the output of the operation is the image. Because, well, conceptually, people say, well, we want the image at the end, so it's natural that we use only, we pay attention mostly to the image token. But because of diffusion transformer, if you go back here, we have the additional output of text token. So by having both of these and then taking advantage of that unique property, Right? So we also have the very nice saliency map. Right? So that's an interesting discovery. So that means there are these capability of diffusion transformer that people have not been using, and by taking advantage of that, we can do some pretty good things. So far we've looked at a concept generated in 2D image. So naturally, a lot of time people want to look at 3D. Yes, question? Sure.
So I have two questions. One is like, does the user need to know what they're looking for? So for example, for the dog with the fold, the user would need to know they need to search for.
Great question. Yeah, the question is, does the user need to know what they're looking for? For example, where we have a dog by a tree, but then a ball gets generated, right? So does the user need to know to look for ball, right? So short answer is yes. And in a lot of use cases, that is okay. For example, imagine you are a company, we would not name it, but a company, they want to allow the user or designer to create images, right? And let's say the company say, well, there are certain concepts we definitely do not want to be generated, maybe like very like blood, or maybe like gun, or maybe prom. So there are things that likely they already is on the list of things that they do not want to generate. So for those use cases, it's already good. And also you can imagine if the designer working in a company, the company itself, they may also have certain criteria that, well, let's say I want to generate the image of a shoe because I'm a shoe company, and I don't want to have like another brand's logo in it, right? So you can also specify, okay, these are the no-go. So yeah, so the short answer is yes. The user do need to know, but for a lot of use cases, that is okay.
Image segmentation.
Great, that's a great question. So how do we compare that with image segmentation? Short answer is yes. So here we're focusing on zero-shot learning, and also particularly for not having additional training on it. So some of the techniques that use training that require training or additional or train on segmentation tasks, so those can outperform ConceptAttention. But then for this particular comparison where we're looking at zero-shot, like extremely low overhead, so our method actually in the paper we compare that as much better than those approaches. Yes, great. Okay, so go back to here. So far we look at generated concepts in 2D image. So not surprisingly, these days people are very interested in 3D, like a particular concept in 3D. And for our group, we are very interested in not only how these approaches are used, but also because of Safe AI, how they could be misused, right? Particularly for concepts in 3D, can people manipulate them, or are they robust? And so we look at it in the context of 3D Gaussian split, and this is work who's in the audience. So is a PhD student in our group, and I call it the satellite office of the Polo Club. So he's by himself. He's doing it part-time, and he is a full-time pilot at FedEx. So by working with him, I learned that pilots have a lot of free time. So apparently they can do a PhD on the side. So if you want to know the secret, you can talk to him. And thanks for coming. So is looking at a vulnerability of 3D Gaussian split, like, and how easy it is to manipulate them. So you're not familiar with 3D Gaussian split. What is it, like 3D GS? So here, show an example video, not from us, from the inventor of 3D Gaussian split. So usually they are used for generating with a novel view. And here you would say, oh, I have a 3D thing. I can go around any angle that you want. The input to generating this is actually collection of images. So that means the user would take some images from different angle of the bicycle, right, in the scene, and then through the 3D Gaussian split algorithm, then you can fuse all these together, and then you have this kind of 3D representation of that whole scene, and then people can kind of go around it. So this is the technology also behind all of the latest thing that you will see, particularly generating an avatar in some like computer vision devices, or maybe robot navigation, how to generate a 3D scene from a sequence of a collection of images. So something to note here that even though it looks like, if you're familiar with 3D rendering and modeling, it looks like it's like a mesh, like some polygons or so on, but actually there's no polygons involved. What it is, as the name suggests, is 3D Gaussians. So what that means is you have these 3D elliptical, sphere, and many of them. This could be millions of them, and everyone has some color. and then some gradient, like Gaussian. Actually, the color will spread out as you go further out. And then all these are stacked together. They're overlapping and so on. So that means what you're seeing here is actually an illusion of the world, and because all these color intermixing, and then they give you the impression that you're looking at a 3D scene. So that means our human eyes are being fooled into, but this is 3D Gaussian splat. So a lot of work on it, and then also the techniques is developed. So we're looking at concept generated in 3D Gaussian splat, particularly how easy it is to manipulate them. You would say, why do we want to study this problem? So the reason is for 3D Gaussian splat, just like a lot of 3D models, often people do not really create them. They might just download it. For example, I want a 3D Gaussian splat model of the bike. You may go to the repository on the web, I download that, and then I put it in my scene that I care about. So that means you, as a user of the 3D Gaussian splat object, may not be the person who generated it. And that is where the vulnerability would come from, because what if the creator of the 3D Gaussian splat version of the bike is up to no good, and they do something bad with the model? Particularly, let's say, I want this bike to look like a bike at ground level, but if it's used for a drone, let's say like high up, like pointing the camera pointing down, the bike would disappear. And that means that the bad actor in this case is, they say, if you have an algorithm, computer vision algorithm, object detection algorithm for like drone use cases, you are going to be all messed up, right? So we want to study this problem. And they say, oh, well, is it even possible? Actual answer is yes. So this is a video. So let me actually go back and play. So here is some 3D Gaussian splat scene. You have three cars, gray car, yellow car, red car, and then it looks fine. But if you go to the back, then this yellow car will have stop signs. Yes. So then we have a self-driving car, and behind it, okay, you're toast, or you get stopped. And if you go to the top and see what happened, oh, it would even disappear. So it can become some row. So actually, you can have it look like anything you want. Right? So it doesn't need to be concrete. It doesn't need to be stop sign. You can have anything that you want. So that means if you are a user of this 3D Gaussian splat model, you really want to ask a question, are you really getting or downloading what you think you're getting? Because you may not. And people with the intention, they could really do it. And also turn out the method itself, again, in hindsight, is not that hard, as in we learned that because the input is a collection of images. So that means we can do is a certain camera angle, as a ground-based angle, you have a benign car, like image of car, that nothing wrong with it. But at a certain angle, then you can inject whatever you want it to look like. So here, for example, looking at the back, you have a stop sign. At the top, you have an image with concrete and so on. And then now you have all this collection of images, all these fitted to 3D Gaussian splat, and you have that view-dependent car. Okay, so that's pretty exciting, also a little scary. But our goal is not to do these. Our goal is to know how to detect them and also how to prevent these from happening. Right? So usually our model is that you want to be a very good defender, you need to know how to be an effective attacker. Right? So that's our latest work on the interpretable AI thrust. In the final few minutes, we want to share a little bit about effort that we're really excited about in AI education. For all the work that we do in safe AI, interpretable AI, something we learned is that for us to make advances in this area, we really need to know very well how this method works. They motivate us on developing a suite of I would call AI Explainer. Actually, we came up with this name pretty recently, or how to build these tools to help students, maybe learners, maybe even experts, like who want to pick up these new techniques. How do they learn it in a way that they really know how approaches work, not only at the surface level, but really go into the detail. So some of our latest work include a transformer explainer, diffusion explainer, CN explainer, and so on. And altogether, these tools now have been used by over 1 million users around the world, and almost 19,000 GitHub starts. So Yeah, I'm going to show you a quick example, not enough time to show everything, but for our transformer explainer tool, as the name suggests, explaining how transformer works. And good news also is that it just got conditional accept last night, yes. So we went to go celebrate a little bit, going to appear at CHI 2026. And like the other tools in our AI explainers, so Transformer Explainer is an interactive tool to help non-expert to learn how Transformer works. So Transformer is the workhorse for all these latest LLM, text-to-image approaches, and so on. So what we wanted to work differently is compared to existing methods, often or resources. Often they're focusing more on the architecture. For example, read a paper, you'll learn about architecture, right? You may learn about the math, and also you might read it in the form of a blog post, maybe too high level. So that means you have kind of two opposite. One is really detailed, like all the detail you want, and then there's a really surface level, like how do you connect them? Unclear. So one to fill the gap is a transformer explainer, offer interactive, very easy to use way where the user can go in, just go to URL, do not install anything, type in the prompt that you have, and then you can see all the way from the input from the left and all the way to output, and then also in the middle, also how the math is working. So here you'll see the overview actually very visual, right? But you can delve into it. I should not use delve because it sounds like an LLM. So how do you go into detail? How the matrix vector multiplication works, and so on. And also very effective is or helpful is you can manipulate the hyperparameter of these models. So for example, in LLM, people often talk about temperature, like this kind of like a magic parameter, like temperature of LLM. You can adjust it live. So the prompt here is the visualization, empower user to, and then visualize is one of the options that you will get. But you can adjust temperature, and then you can see on the right-hand side how the next token, including visualize, the probability would change. So temperature, lower temperature, that means more deterministic. Higher temperature, that means the distribution is more flat. So what that really means is you can pretty much get any next token that you want. What get eventually sampled is the probability. So this is something that a lot of people do not know about because they just consider temperature as like a creativity. Right? So a very kind of using like a human sounding name, but technically what's happening is you're actually changing the probability distribution. So you can do it live. You don't need to have any GPU or spin up anything, and then you can play with it. And this kind of interactive capability is very, very important because for a new learner, if they're thinking about, oh, what does all these mean? You can read about it in text, of course, but versus like seeing it, how the computation actually working and then tying to the math in real time, extremely powerful. And also, an important feature is that even though we have a high-level visualization, we can expand it going into lower level and details and looking at, for example, the attention mechanism. How do you go from dot product to the scaling and masking doing a softmax? So you can expand and collapse so that you can first get that overview and then get in the lower level details. Right, so this is only one of the examples. Yeah, different part of the model, you can do something similar. So for transformer explainers, so now it's used by I think close to 405,000 learners and around the world, and also now is used in quite a few courses in different universities. So this is something that we're really excited about, and then also is something that we think is a model that we can continue to build on and have more tools on it. Something to share personally is a lot of these tools that we build, including Transformer and also our earlier CNN explainer, we use the same or have the same motivation where some of the PhD students in my group say, oh, we want to do more text-to-image or LLM. We want to do like more like deep learning and so on. And as an advisor, often my first thinking is that, I need to learn this new thing that I did not know about. And usually our approach is that if I want to be an effective advisor, I think it's important for me to know very well. And then naturally, we try to learn about, are there existing resources that can do that? And scientists know, at least at that time, so that motivates us to build this tool. Originally started from a more selfish reason. I said, okay, I need to know about this. But now it turned out that, okay, so it's not only benefiting ourselves, but also it can help learners around the world. So CN Explainer is one of the early ones, actually even earlier with GAN. I think GAN you may not hear about as much because it's superseded by diffusion in many ways. So GAN is generative adversarial network. So again, generating images or data point that looks real, but it's not. This is actually one of the very first one that we co-developed with Google. And also we have Diffusion Explainer following a similar approach. All these run directly in your browser and do not need to install anything. And now from experience, we know this is a very powerful way because as a learner, you can imagine you not having to install things, just not having to like get GPU instances. This is a huge thing. And also for instructor, myself included, it's just wonderful. You go to a class and I don't need to prepare anything and just say, hey, student, bring out your laptop and everyone go there and then work on it together. So that's great. There are limitations, however. You'll notice that all these tools, Diffusion Explainer, Transform Explainer, they are designed only for a single model, right? So natural question to ask is, well, there are even more models, like Transformer, yes, it's a workhorse, but there are also now variations and so on. So how do we extend these approaches to more models? So we are making a little bit of headway in that. So ML is one other approach where we can generate automatically generate these animation based on code. For example, here you want to communicate like CNN. So we can have code that is very much like PyTorch. So at the bottom here, like PyTorch, where the user can use syntax they're already familiar with, and then they would get the automatically generated visualization. So still work in progress, a lot of work to do. Ideally, we want to have this generation very similar to the tool like Transformer, Explainer, and so on. So much more high quality, much more interactive. But hopefully we get there. So today, summary. So we show a few examples in Safe AI, Interpretable AI, and also AI education. So all these are things that I continue working on, and hopefully I convince you they are all very, very important work to work on, very exciting, and also hopefully a lot of you will work on it because I think we need more people doing this work. So with that, thank you very much. I think it's questions. Yes. Yes.
For the LLM attribution, I'm just wondering if the attribution is like causal or is it more like based on like retrieval?
Oh, the question is about LLM attributor attributing the generation to the data. Is it causal or is it based on? I forgot. Is it like more of a causal?
Like just matching like what each.
Oh, is it causal or based on matching? Actually, neither. So main idea is that the algorithm that we're using there is that it does need to do a pass through the training data. So and then the main idea there is to look at which training data would affect the output the most. So there is some causality there. There also some query aspect there, but it's more looking at the laws, like changing in the laws, how that affect the generation. Yeah. Yeah, so it's computationally it can be expensive because it does need to go past the data point. So which is why I mentioned like for companies that have the capability of really going into the training data, then they would be more equipped to do that. Yeah. Okay, great, thank you. Oh, yes.
I guess this still discussion about the first project with the basin, but jailbreaking, like the standard way to do it is to move the models out of distribution. I don't know if you think there's a way to like address these basins and like avoid them, or maybe we restrict fine tuning so people can't at least do that. I don't know. Is there a way to stay safe out of the basin?
Oh, okay, great question. So the question is there a way to stay in the basin? Say out of us? Oh, I think.
Out of the basin, I don't know.
Oh, yeah, great question. Widen the basins, right? So the thing there is, we did not study how to widen it. Actually, I think the extent of how much we can widen the basin unclear, because currently what people are doing is they have guardrail. In a lot of ways, like personally, I think of guardrail often it's kind of like bandages, as in, okay, you already have the data, you fit in all the data. Best way we think is probably when you start with the data so that you don't even have that problematic issue in there, because now all these guys will just say, oh, you should not spill this out. You do not want to generate this by this thing. So so that means how wide the basin in a lot of ways really tied to both the data and then also what's the coverage of your guardrail. I think so far we can probably tell the guardrail coverage is not very comprehensive because no matter how many guardrails there are, we always see like it's going to steep pass. So I think it's very important to work on, and I think I don't have an answer for that, and I think the visualization approach right now is not really restricting it, more to just let people know, hey, it is going to break, and then the break is catastrophic, like it just breaks suddenly. So thank you for the question. Yes.
So I really like the last part of application, like this visualization for application, and it's very fascinating to see the huge amount of visitors and adoptions of those tools. I want to know, like, in this process, so many people are doing this like particular set of tool. Do they have any feedback or comments to this? Where do you see the potential limitation of this kind of techniques? By fixed, I mean like everyone's seeing the same interface to explain transformers, but like usually students get stuck in different places. So do you have any kind of shared patterns where the community actually provided to your different applications?
Oh, great question.
Yeah, so the question is asking about these suites of AI explainer tools. Are there any like feedback from the users, maybe about like what is effective or not, and also, like, are there patterns like in developing this? That's a great question. Actually, that's one of the questions from the reviewer. Reviewer number 2. For those of you who submit to Kai, or to any conference, a reviewer number 2 usually is the most critical. And then great question. So then at the high level is very natural to think about, all of these are explainers, right? So are there something unique about each of them? I think at this point, the answer is yes. So there are certain things that design strategy, for example, all of them start with like overview first. And we found that is a more gentle way to ease a user in. And this is actually using human-computer interaction principle, information seeking. Like when you show something new, some new information, you want to provide some people some mental anchor, like in this case, overview. So that, I think, is one pattern, if you would, cutting across. But after that, then I would say currently all these tools have their own unique kind of visualizing technique. For example, for transformer explainer, like here on the left, actually one of the reviewer asked is that, how is it special? So through the rebuttal process, actually we got us thinking a lot more. So I think we have that idea, but in the original version we didn't write it out as much. But in the rebuttal we wrote it very well. Is here, transformer explainer, we actually need to visualize the token, the text token, particularly the token from the input all the way, like through this kind of band-like visual, all the way going from the top, going through every component in the middle that might shrink and then expand, and then all the way to the output. So that is new, because in images, for example, CNN explainer, you don't need to solve that challenge because you already have the image. Image is relatively easy for people to, they just see it, they get it. But then for the token, for example, in transformer explainer, that is an additional thing that we need to think about. So in that case, there's not really a pattern there that's unique to transformer explainer. So actually finding the pattern would be great. And actually we want us to be not one of the few groups that would build these tools, because it takes a lot of time to build like transformer explainer, at least 6 months and so on. And there's limited time. So it would love for more people to be able to build this. And so maybe now on the generative AI tool, they're advancing enough, we can automate ourselves out and creating. But I think that's a great thing, because there's still a strong need. Like if we want to make advances in these techniques, like pushing the envelope of innovation, very, very important to have a good education tool. And yeah.